shall we just look at the problems, go through them together? Is that a reasonable plan? In fact, I just realized there's something. Let's just switch it off. Zoom record.
Yeah.
Okay, fine. So that these pearls of wisdom can be very permanently available. Very good. Okay, so let's do the first step. As we are suggested, we should choose a vector, right, in here, just any vector. So just exactly like in Gram-Schmidt. Well, Gram-Schmidt is you have usually a little bit more information on this, but never mind. This is a minimal version of Gram-Schmidt. So we choose that's the first step, and we choose f in V such that omega EF is not equal to 0. All right. Now, this is always possible because omega is non-degenerate. Okay.
Maybe we should suppose that it is equal to 1 from the beginning.
That's exactly what I wanted to say. That's exactly what I wanted to say, is that without lesser generality, we may assume omega EF equals 1. So that is possible. We just renormalize F. As soon as we have something non-zero, we can just divide by this something, and we'll get a renormalized F for which this value is just 1. So that's the first step. Okay. Now let's step 2. Define let. So this is just a definition. I want it to be, I take the span of E and F, which is a two-dimensional subspace in V, and I take its symplectic orthogonal subspace. So this is equal to the set of all V in V, so that omega EV equals 0, and that's also equal to omega FV, right? Because E and V are a basis for this, so if it's 0 for any element in this subspace, it's equal to E for E and F. All right, so let's notice we have clearly V intersection with this two-dimensional subspace is just 0. Okay, because E and F are definitely not in this V prime, so the only intersection is 0.
It's
right,
not
so,
enough to see that E and F are not in V prime. We need just to multiply arbitrary vector from E times alpha plus F times beta to E maybe.
Yeah, I can do that as well. And so that's, I was just saying, if I take omega times alpha E plus beta F and say that the inner product with the symplectic product with V is 0, then clearly that is going by linearity, that's going to tell me that alpha is basically equal to 0 for any alpha and beta, and that it amounts to this. It's just exactly the same.
Yes.
Okay.
So I just heard that you say like E don't belong to V prime and F don't belong, then linear subspace intersect by
That's
0. But
true. You are right. Yes.
not true.
Yeah. It's enough to show that E and F are because they generate. It's all linear combinations also will not be there. Right. Okay. So now what I want to do is I want to consider this space. So I take V prime and I take omega restricted to V prime. Right? And the claim is that this is going to be a symplectic space as well. So it'd be a symplectic space of 2 dimension less than V. So obviously this omega restricted to here is clearly going to stay skew symmetric. So the only thing I need to check is that it's non-degenerate. So So check omega v prime is non-degenerate. Non-degenerate. So how can I do that? I'll just let, so for u in v prime, let us suppose that omega restricted to v prime of u and v is equal to 0 for all v in v prime. Okay, well, this is equal to, this is just the same as omega of u v. And if omega u v is equal to 0 for all v in v prime, that tells us that, let me just try to hide this.
That tells us that it's true for all v because v is direct sum of.
Yes, you're right.
Right.
But I mean, you can formulate this in many different ways. This would be the advantage of doing it offline, Anton. This is why I prefer to do things offline, because practically speaking, the only reasonable way to do it is just to present one of these things. And that is just to say, we see from here that if u and v, if omega of uv is 0 for all v in v prime, then clearly u is in here, right? But u is in here and the intersection is 0, so this tells us that. So this tells us that u is in EF, but so this tells us that u is equal to 0, and so it's non-degenerate. So it's a symplectic structure too. So we can now just do exactly that. We can just repeat the same thing we did for v. We can do it with v prime, and we can do the same thing and get to v double prime and so on. We do it n times, and we're going to get the symplectic basis, right? So we're going to get, there should be a way to get rid of this. I know there's, no, I don't know, stick it there. So we get repeating this process, repeating this procedure n times, we get E1, En, and F1, Fn symplectic basis. Okay. Now I'm, so that's the first question. Right, I don't remember whether there was a certain moment where I preferred to jump to, oops, okay. I'm sorry, but you can see that I've got this thing right in the middle of my screen. I don't want it to be there. Ah, good, it's gone. Okay. All right, so let's have a look at question 2. So question 2 is, by the way, what is question? Let me see what is question 2.
So now we have a different form of symplectic basis when first n vectors are fixed to Lagrangian subspace.
Well, Anton, we are looking at vector space. We're not talking about tangent space yet. This is just symplectic.
I didn't say tangent. I said fixed. I said now we are looking for different symplectic bases for V, where first n vectors are fixed Lagrangian subspace. Yeah.
So I'm sorry. We are still in problem 1, right?
No.
Yeah.
No, we've already solved the first
So,
problem.
Anton, your comment is about problem 2, right? Or,
Yes.
sorry, well, fine. Okay, so we need to go to problem 2. So we need to go to problem 2, which is here, right? I was just checking. So we suppose that it's a vector space of dimension 2n, a symplectic vector space, and we suppose that L is a Lagrangian subspace. And we want to show this is a symplectic basis for which, okay, yeah, that's right. Yeah. Sorry. Okay. So let's start off. So we have L is Lagrangian. L in V is Lagrangian.
Yes. Let's
So that
choose.
means-
Oh.
Just a minute, Anton. Let's just write it down. So it means that L omega equals L. Okay, go on. Tell me, Anton.
So let's choose an arbitrary basis for L, call it x1,
All right,
x2,
all right, let's do that.
etc.
Very good. That was my plan also. So Anton, did you already solve this?
I think yes, but I didn't
I believe
write
that you can.
this.
I believe
so
that you
I
can do
just,
it in your head. I can believe.
yes.
But anyway, okay, so let's let Anton produce this. So choose a basis for V.
X1, X2, for L.
Okay.
For L.
For L. Yeah, you are right. You are right. Sorry, for some stupid reason, I like using E and I like using E for basis. I don't feel comfortable writing. For me, X's are coordinates. They don't look like the vectors. But it's okay. So I'll write it that this is a basis, right? Okay. So this is
Yes.
this is the statement that is a basis. Okay.
Yes.
And then?
And now fix any vector, and now take any vector not from L. And we know that it don't belongs to L
Okay.
orthogonal.
All right. Suppose, I don't know where you are going with this, but anyway, suppose V is not in L. That implies that omega EI V is not equal to 0 for some
No,
E.
no. Of course, it's not like easiest way. Easiest way is let's pick any vector that has that has scalar product 1 with E1
Okay.
and 0 with
Anton, what our objective is to find a vector which has scalar product 1 with E1 and scalar product 0 with the other.
with other ones. So
I mean, it's a little bit non-trivial, by the way. So I mean, if you did it, maybe it's kind of, I can understand that you look at it as something not very, very difficult, but if you didn't go through the details, I think we will not get it right this minute if you improvise.
Yeah, actually, it is not so well. It can be done, but well, but it is much harder to present like second one or third one.
You can kind of go through.
The idea is that we have like n other linear independent vectors.
But let's write it down then, Anton.
V.
All right, let's do it.
So it's some matrix, yes.
Just a minute, Anton. So you're saying that we have some other vectors, but that's exactly my plan. And by the way, Simeon has also done this. So he has a nice solution already, probably. But let's just write down. So we'll extend it. Let's see.
Kind of coordinate-less solution. Yeah. Without I have solution without picking any basis actually.
Oh, but that would be very nice. I would love to see something like this. Let us continue with this one, because don't forget that the question asks us for a basis, right?
Yeah, but well, my solution presents them.
No, but I'm interested in your solution. I'm very interested in your. Maybe I just give you the screen or something. But,
well, I can present you.
Let me just finish this one. Let me finish this, because we started. The question asks for a basis. It's kind of natural. But I would like to see your solution because I can believe it's nicer. All right, so let's just start. We'll just do the simplest thing is to extend to a basis for V, right? So I'm going to write that V is E1 up to En, and then we'll come to your solution, Simeon. So what shall I call these ones? I'll call them lambda 1.
So now we draw matrix with like n rows and columns, and on EG there will be like EI omega applied to EI and lambda J.
Yes.
So idea is this matrix is like
absolutely
non-degenerate.
And as you'll see, this is actually one. There's one solution to do this. This is one solution to do this, and we can go through that. But actually, you can also do something quite, you can do it, something quite nice here, which may be what Simeon is doing. I don't know, we'll see what Simeon is doing. But the point is that as soon as I have a basis for the whole space, then I naturally get a dual basis for V star, right? So here is one variant. The other one would be to do what you suggest, Anton. So one variant is to say, let's take a dual basis. So dual basis for V star is equal to the span of. By the way, let's just do this a different way. Sorry, let's call, because it'll be neater if I call these. If I call these En plus 1, e to n. Okay, and then it's epsilon 1, epsilon 2n. And the dual basis, well, it has the standard property that everyone knows, is that EI acting on EJ is equal to delta IJ. Okay, or I can write it as the pairing. Anton likes to write this like this. It's a pairing between the dual space and the dual space and the space. And now, so of course, epsilon 1 paired with E1 is 1, and that's so on. And if I define Fi to be equal to this omega flat inverse of E of epsilon I, then I get the basis. Then that tells me that that V is equal to the span of E1 up to En and F1 up to Fn with omega EI Fj equals delta Ij and omega Fi Fj will be 0. So that's a constructive way to do it. You can check that last thing. It's a little exercise. But the alternative is to do what Anton, just exactly what you said. And I wrote this down.
Excuse me. So this first idea uses identification between L
V
between
and
V star.
Yeah, V and V star, they identified, this is an isomorphism, right?
Yes.
This map is an isomorphism. So therefore, these Fi's, these epsilon I's, this is for I equals 1 up to n. So I don't care about the last ones. So for I equals 1 to n, I take the inverse image of these epsilon I's. They were linearly independent. So these are also linearly independent. And this thing here, I mean, omega Fi, which this accepts another vector, is equal to epsilon I. That's exactly what this thing means. So this thing here, when it hits an EI, it gives me it's an EJ gives me delta IJ, and if it hits one of the others, then it gives me, if it hits one of the others, then it gives me 0. So alternatively, I can do just what you said, and
but
for this,
it's clear that they are orthogonal to each other.
Say that again.
So is it clear that Fi is
no, exactly as I wrote this down? I don't think it's trivial, but the point is I produced this solution kind of in my head during the morning. I realized that this is not complete, but I believe it can be checked as well. It's just a little exercise. Check that. But let's look at this. I'm going to do the one that Anton suggested now. Okay. And for this, it's nice to introduce some extra notation, which I think is useful. So let's introduce Fi. So I've got these ones here. So I'm going to say that it's equal to, and for this, actually, I prefer, let's write n plus I is equal to Fi hat. Now, it's just a little change of notation. So Fi will be equal to the sum from k equals 1 up to n, a linear combination of the e's, so that's ek mki, plus fk hat nki. All right, and I'll write this f. So f is a matrix which consists of these vectors. So f1, f2, and so on equals e m plus f hat n. Okay. That's essentially what you were suggesting, Anton. Okay. And now, if I want to take omega, so this is a nice shorthand notation for all of this, and I want to take omega of et etf. This combination, it represents ei fj. So this thing is supposed to be the identity matrix when I put in all the possibilities of this. And now if I just substitute in here, so I have omega of et, and then I put in here em plus f hat n, then this is 0 because L is Lagrangian, and then this is omega et f hat n. And now I just choose n to be the inverse of this matrix. So this is a matrix with entries omega ei f hat j.
You need to prove it's non-degenerate. It's follows from Lagrangianity.
Yeah, sure, we can prove it's non-degenerate. So then we'll take, let's check that omega etf is non-degenerate. Okay, so let's think, how can we do that? Just a minute.
So for this, we need to understand that this matrix is like matrix of pairwise products ei times fj, and if some like linear combination of rows exists, then there is a vector which is linear combination of fi's that like annihilate whole.
Yeah, that was my plan also. That was my plan. So if I want to take, so in other words, it has a 0 eigenvector. It has an eigenvector with eigenvector 0. So suppose omega of etf f hat, let's say v, it may be more convenient to take it the other side, but anyway, let's hope this works, equals 0 for some v in Rn, right? Some non-zero v. Okay, so we have, just a minute, let me see. So what do I want? I always get lost when I try and do this. Aha, so that implies, so this equals omega of et f hat v. So if you want to just understand, if you find it difficult to understand this, just think that this is just a shorthand for many components. So this is ei fj, and this is the sum over j with vj. So this, I put the sum over g of this, and this is this thing is a vector. All right, so this thing is 0, but it's 0 it's a zero vector. This thing is a zero vector. And so in other words, it has zero symplectic product with every EI is zero. So that means i.e. FV is in L. When L
Excuse
and
me.
omega is equal to L.
I think you have too many notations for this. I kind of mixed them up. What is this omega of something? How can it be vector when omega is two form?
So omega is a two form, but I introduced this notation just to save lots of writing. You may have noticed, Anton, my writing with this tablet is really disgusting. So if I can make it more streamlined, I can make it more easy to understand. So here I'm keeping the index notation, right? But I hope it's clear what I mean when I say that this is encoded in this statement. Is that clear? This is the same as that. It's just a shorthand notation for this.
Okay, so
okay,
F bar is like F hat is some linear operator with image which is complementary subspace to L.
I wouldn't say it's a linear operator. I would just say that it's an array of it's just F. Right, let's write it here. F is just this row vector in which each element is a vector. So it's F1, F2, Fn. So it's just a way to organize things so that that means that if I organize my F's into a matrix equation like this is just the same statement as I have here, it's just identical. Right? This statement here is the same as this statement here when I'm using this convention. And so now when I write this, what I'm thinking of here is I'm thinking of a thing where I have I'm producing here a 2n by 2n matrix in which, well, an n by n matrix. I'm producing an n by n matrix in which the ij component is the symplectic product of EI with Fj.
Okay.
So it's just a shorthand way of writing things which hopefully are easier to read because my writing is so bad. And when we do things offline on the blackboard, that will be improved, amongst other things. So, of course, this matrix, of course, I'm allowed to make it act on a vector. And when I do that, it's the same as, because this is the ij component of this is supposed to multiply vj and sum over j. It's obviously the same as that. And that just tells me that this guy is in L, but we can't have that, right? Because if this is in L, then it means that there's a linear combination of these F's that is in L, and that's not permitted. Okay. So that's a contradiction. So it follows. So therefore, omega ETF is non-degenerate. And we just take n to be the inverse of that matrix. And that's that. But now,
sorry, could you back to the previous page?
Could I do what?
Yeah, I was a bit lost.
Tomoki, I'm sorry, just say it again. I didn't understand.
Yeah, sorry. Could you back to the previous page?
Go back to the previous page.
Yeah. Yeah, which hypothesis guarantees F is not in L omega?
So this F here is, just a minute, let me try and keep track of what we're saying. So I want F. Well, there is no high, I'm free to construct it, Tomoki. I'm given L Lagrangian, and I'm going to construct a basis, a symplectic basis for V, in which L is the span of E1 up to En. So I'm free to construct this F.
Mm-hmm. Okay.
So I start off by extending the basis from V to this, and then I introduce. So I'm calling F hat this second group of E's. I'm confusing myself with the notation. But Fi hat is the second bunch, right? Is these guys.
Okay.
These are F.
Okay, yeah. Now I see it.
And now I'm free to do this. I mean, I'm free to do it.
Yeah.
But what I'm not free to do is I'm not free because this F hat is something fixed. Well, I mean, there was some freedom here, but it's just F hat is any extension is the vectors which extend the basis. So I get a full basis for V. And all I'm saying is that however I do this, whichever choice for these F hats that I do, I'm always going to get something where this matrix is non-singular.
Okay. Now I got it. Yeah.
And by the way, because this is related to a later problem, and you asked a question about this in the chat, the freedom in the choice of these is precisely the possibility to add elements of this collection, right? So if you take the span of these, I'm going to get something in this span of all these Fs, plus possible additions of guys in here, because that doesn't change the span of the overall thing. So these are defined modulo addition of vectors in here. And depending on the choice I make here, I'm going to get a different choice there. Notice that, of course, the dual basis for V star depends on this choice. Okay. So this is non-degenerate, and I get that. And then, well, after that, I've got N. So N is fixed. M is not determined yet, but N can be determined now if I take omega of F. This should be 0, right? So I need this to be 0, but let's just see what this is. So I have omega of E M plus F. By the way, sorry, that should be transposed. So it's M transpose E transpose plus N transposed F transposed with EM plus Fn. And as I said, this is just a shorthand notation. So this consists of, you could just think of it, if you expand it, you'll just have lots of indices. So if I multiply this out, so I get M transposed omega E transposed E, all right, which is 0. Plus,
I'm sorry, we should have hat on F probably, or maybe I missed.
Thank you. Yes, you are absolutely right, Anton. Thank you. Thank you. So, and now I have omega. So I have N transposed omega F hat transposed E M plus M transposed omega E hat E transpose F hat N plus N transposed omega F hat transposed F hat N. All right, so now that one is 0. Here, this combination is the identity, right? Because we chose N to be the inverse of this. So that's the identity. And then this is just the transpose of that, but there's a minus sign, because this thing here is minus the transpose of this thing which I get in there, which is just minus the identity. So this is minus the identity. and I get equals M transpose minus M plus N transposed omega F transpose F N. Okay, so this is something that you can calculate because F hat is something given. So this thing is given, N is known, so this is given. And so N is just any solution of this. And notice that M is defined modulo possible addition of a symmetric matrix. So that's something worth noticing. So the general solution of this is M is equal to minus 1/2 N transposed omega F hat transpose F hat N plus S, where S is transpose equals S. So this is the general solution. Okay, so we have some freedom. We've got various steps where we had some freedom. So the first thing is that we could choose these F hats completely arbitrarily in such a way that this provides a basis of the full space. And then afterwards, we should allow the possibility to add terms from here. And then afterwards, we can again add terms from there by multiplying with a symmetric matrix.
Excuse me, I think I have a very simple explanation for all these things. It sounds like when we change fi to, for example, f1 plus fi, we act like using linear transformations on rows of this matrix, and there is two cases. We can either get zero vector, and in this case it will be zero row, I mean, and in this case it will be like vector not in L but orthogonal to whole L, or we can get identity matrix and it will give us like good pairings between F's itself and between Fi and EI.
I'm sure you are correct in your observation, Anton. I just didn't follow it properly. But if other people did, that's obviously helpful. Thank you. But is it maybe worth, at this point, I will give the screen to Semyon. He can...
No, I'm sorry, I was a little bit wrong because we need to get that Fi is orthogonal to Fj too.
Okay.
Yeah, sorry.
All right. So let's offer Semyon a chance to share the screen and show us his solution. If you want to do that, Semyon.
Yeah, I don't know if I should, but I can.
Well, I would be happy. I mean, you know, let's see a solution which doesn't involve any basis. It's probably a much cleaner version. It would be nice. Let's see.
Give me one. Yeah, so I hope you can see something.
I think we can see. Yeah, I think so.
Yeah, great. So yeah, so I'll present my solution in two steps. So first of all, maybe so we have Lagrangian L. I'm sorry, L inside of V. So let's suppose just for a second that that there exists another M, which is again Lagrangian. And transversal to L. Yeah, it is always true, but
that would have to be checked, right?
Yeah, we will check it after we'll use it. Yeah, of course. Yeah, but if there is such a transversal Lagrangian subspace in V, then it is quite easy to construct the required basis, just because since they are transversal.
Using omega.
Sorry, yeah, the pairing using omega is non-degenerate. And therefore, we have the following isomorphism from M to yeah, maybe let me write it like this. So we have M is subspace in V, V is isomorphic to V star, and we have surjection from V star onto L star, and this map is isomorphic. And yeah, and actually that's all, because now I can take any base of in
So
L.
you have your omega, you have omega flat in there, which is exactly the thing.
Yes.
Yeah.
And then the dual, well, I can take a base of M, which is dual to E1, En. Yeah. Let me think.
I think that this is the same as the solution 1 in disguise, to be honest, Simeon. That's what my impression.
Yeah, just
I have a very quick question. Can M be an arbitrary complementary subspace? So is any complementary
so.
to Lagrangian itself?
It won't be Lagrangian, I guess.
No, but the point is the point of the question was exactly this. This is exactly what was presented in my first variant, right? My first variant, M, it was the same as your explanation, but M was not Lagrangian. It was just an extension. It was an arbitrary complementary subspace.
Yeah, but I guess.
And then you could construct the same chain. But the thing which is not free is to say that the symplectic product between the F's would not be automatically 0 in that case.
Sorry, yeah, but yeah, but in this case, I guess the orthogonality of Fi's is kind of
yeah, it's free.
Yeah, it's trivial. Yeah.
So my question is exactly if we take an arbitrary complementary
not sure
subspace, there can be non-orthogonal vectors in it. Yes.
Yes, yes. I guess it is, well, for arbitrary.
So.
If you take an arbitrary extension, if you take arbitrary F's, then you can do what I indicated, which is to take a dual basis to the whole basis. So you take a dual basis to E1 up to En, comma F1 up to Fn. This dual basis depends on the choices of the F's. And then after that, you can take omega flat inverse of the first N terms in your dual basis. And this will give you your symplectic basis.
Yeah, but in this case, you need to check the orthogonality of
the F's. Yeah, but here you also have something to check, by the way, Simeon.
Let me think. I guess it should be. One sec. No, I need not to check orthogonality, but because it is hidden in.
No, here you have a different thing to check.
Yeah, I have just well, if I suppose that there exists such Lagrangian subspace transversal to L, then there is no need to check anything actually. Yeah, because orthogonality of Fi's is trivial since M is Lagrangian. They are orthogonal to each other. Yeah, so the only thing I have to check that there exists Lagrangian subspace which is transversal to L here. So yeah, so should I do it or yeah, I mean, should I finish my solution or it is already clear? Maybe so I can, but
continue, please. It's not clear.
Well, the point is that suppose that you take that. Wait a minute. Suppose you just take any complementary extension, then the way to construct from this a Lagrangian one would be precisely to add terms from L, which is exactly to add this term EM, which I had in my. So exactly what you would do.
No, I would say that if you take arbitrary, then you should add not only subspace from L actually.
Yeah. Okay. Anyway, so Anton Sorokin, he wants to hear the continuation. Let's hear the continuation. Why not?
Yeah. So
if it's easier than what was like computed before, yes.
Yeah, there is just few rules of solution. So yeah, I claim that such L does exist. So let me show why. So take any M which is isotropic and whose intersection with L is 0. Yeah, and well, of course, such maybe called M prime. And
For
yeah,
example,
so
zero
what
dimensional.
sorry.
For example, zero dimensional space. Yeah.
Yeah, for example.
Isotropic and okay.
Yes, of course. Yeah, and take so we have such isotropic M. And
Simeon, can you remind us what isotropic is? So is it M in M omega or omega M?
Contains in M prime omega orthogonal.
Okay.
Yeah, and one extra condition that it is yeah, so this is my set. Then take M from here, which is maximal. Namely, it does not contain in any larger isotropic subspace. Yeah, and I claim then M is Lagrangian.
So you put an ordering on this.
Yeah, of course. So they are kind
they
of.
They are ordered by containing set.
Yeah, and I claim that any maximal element is Lagrangian.
Yeah, that's nice.
Yeah, so yeah, I should prove it. So if it's not, then its orthogonal is co-isotropic which properly contains M. Yeah, and then let me see. Yeah, so I have projection from here to omega modulo M. Let me see just for a sec. Yeah, so I claim that now I can take any one-dimensional F, which is orthogonal to, I'm sorry, which is transversal to projection of L here. Yeah, so I have, I'm sorry, so I have intersection of M omega and L, and then I can take any, so I can take its projection here, well, its image in the quotient space, and take any one-dimensional subspace which is orthogonal to this image. Yeah, and therefore the preimage of F would be the larger quasi-tropic. I'm sorry, the preimage of F would be larger isotropic subspace containing M.
Mhm. So M would not be maximal.
Sorry?
So M would not have been maximal.
Yes, yes.
Okay. Good. Okay. So się uwidzisz? Co to tam?
Yeah, so now, so
Okay.
so I should now stop my sharing.
All right. So if you return to the next question then. Sorry, we have just done A, right? Right, okay. So now, I don't know why I'm jumping like this, but yeah, I would like to jump to do the question about 3. I'll come back to this, okay? I'll come back to this. All right, so let's go to 3. So we're given omega, which is a map from V times V to R. Okay, and we write SPV to be the subset in GLV, which is defined to be, okay, so this says, well, G in GLV such that omega GU GV equals omega UV for all UV in V. Okay. So, and we want to check that this definition generates a group. So we want to check that if, so they are in here, we need to check that it's closed onto composition and it contains inverses. So let's just take GH in SPV. And let's have a look. So we'll take omega, GHU, and GHV. So GH is perfectly well defined because G and H are both in GLV. So this thing acts on a vector in R2M. It acts on V by standard composition because GLV defines an action. So this is equal to omega of G, HU, G, HV, just by the property of GLV acting on there. And now, by the property that G is in here, this is omega of HU, HV. So that's because G is in SPV. And now this is equal to omega of UV because H is in GL, SP. Sorry. SPV. Okay, this is because G and H are in GL. Okay, so that tells us, so i.e. GH in SPV implies that GH is in SPV. So it satisfies the decomposition property. And your associativity property will follow by the fact that these are both in GLV. Now, if I want to look at omega of UV, this is equal to omega of GH G acting on G inverse U G inverse V, and that is equal to omega of G inverse U G inverse V. So I can see that, so G in SPV implies that G inverse is in SPV. So it's a group. Okay, and now I'm going to keep the same notation as I introduced before. So if I have let's suppose that so let's write writing U. So U is an element in V, right? So because U is an element in V, I can write it in this form. I can write it as E. Remember what E was? C plus F eta. Right, where E and V, they represent this symplectic basis. So I'm not going to keep reminding you of this every time, but I'll do it just this once. So E is equal to E1 up to En. F is equal to F1 up to Fn, and Xi and eta, they are in Rn. So this notation here represents these linear combinations. The obvious, it just says that I've got a linear combination of E's and a linear combination of F's, and I'm writing it like that. So now I'm going to write that G of U, well, saying that G is represented by that matrix, which is given in the problem. To say that G is represented by this matrix, it just says that I'm supposed to write it in that basis and then act on it with this 2n by 2n matrix. So it just says that GU is equal to E on AXT plus B eta plus F acting on CXC plus D eta. Let's go back to that. And that is equal to EA plus FC C plus EB plus FD eta. So I can either think of it acting on the change of basis. This represents a change of basis formula, or acting on the components in a fixed basis. But I like to think of it as a change of basis formula. And so now I'm going to have, if I compute omega of U, sorry, let's write omega of GU GV. So this is equal to well, if you just, I'll maybe skip the details because it corresponds to the pairings between the E's and the F's, which is easy to write. So we end up with C transpose A transpose. I guess that comes from here. Yeah, okay, that comes from this representation here. C transpose A transpose plus eta transpose beta transpose. Right, by the way, sorry, and V, let's write V is E C prime plus F eta prime. So that will be like that, acting on C prime plus D eta prime minus So now I should write C prime transpose A transpose plus eta prime transpose beta transpose C minus plus D eta. And now if I organize it into groups, I get C transpose. So what's C transpose? With C prime, I got A transpose C minus, all right, well, if I just take the transpose of this guy here, I'm going to have minus C transpose A C prime plus eta transpose. How many do I have with eta transpose and eta prime? So I get B transpose D minus D transpose B eta prime plus C transposed with eta prime, so I've got A transpose D minus C transpose B plus eta transpose C prime, so that B transpose C minus D transpose E minus D transpose B. No, not the minus D transpose A.
Excuse me, I remember the easiest way to do this. It's just block matrix multiplication.
Sure, it's just equivalent, Anton. It's just equivalent. But you say it's easier. I mean, it's the time it takes me to write down on this painful thing. If we do it on the blackboard, it will be easier anyway. But of course, these things are all equivalent. They're just equivalent. I don't think it makes sense to say it's easier. It's just it's not a very, very difficult calculation. You can choose your different approaches, but you can see from here that if you want to compare this with omega of U and V, omega of U and V is going to correspond to A being it's going to correspond to A being the identity, D being the identity, and B and C being 0. So this should be an omega UV is going to be C transpose eta prime minus eta transpose C. So therefore, we require A transpose C equals C transpose A. We require B transpose D equals D transpose B. And we require that this thing is 1 and that this is the same, this is -1. So they are the same statement. So we require that A transpose D minus C transpose B equals IN. Okay. So that's the matrix representation of SPV. I even wrote it down here, it's the same computation. So that's straightforward. So now if I come back to the rest of it. So now I want to go to problem 2b, I guess, and it's 2b. So L Lagrangian, L prime Lagrangian with L prime L equals 0. Somehow I have a feeling that this is the same as Simeon's solution in disguise. But anyway, what I want to do is I want to write a definitely I have a change of everything in V can be represented in terms of the basis E and F. So I certainly have the E prime, which is supposed to be a basis for L, for L prime, can be represented as a linear combination of these A's and F's. Right, so if E is a basis for L, and F is some complementary terms for which make a symplectic basis for V, then I can certainly represent E prime like this, and I can represent F prime like this, where in any case F prime is not even uniquely defined. It's defined modular combinations depending on E prime. But now I have that E1 prime, En prime intersect with E1 En is equal to 0, because that's what we're told, right? So that requires that the determinant of this guy is not 0. So the determinant of C is not equal to 0. And the way you can do that is just exactly the way I did it before. So you suppose that it is 0, then there will exist a V so that CV is 0. And that means that E prime V is going to be EAV plus FCV, but this one is 0. So it means that E prime is a linear combination of E's, but that's excluded from the hypothesis here. So it's already excluded. So this thing cannot be 0. So I'm not going to write that down. It's just the same as what we did before. So so if I write, so it follows that E1 prime up to En prime, the span of this, right, is just the span of these guys, but it's just the same as if I take a different linear combination, different arrangement of them, in which I've just assumed that C is 1. So this is the same as EAC inverse 1 EA, sorry, that's a mistake. Plus F1 EAC inverse N plus Fn. So I can, in other words, I'm assuming without loss of generality that C is identity. That doesn't change anything given that it's non-singular. I was just going through the details, so I can assume that C is the identity, and now or equals, yeah, and I can call this. Actually, I've got what I've written here is much clearer, so I'll write it like that. I'll write it like that. So I have E tilde 1, E tilde N with E with the tilde equals E AC inverse plus F. So in other words, I'd assume without loss of generality that C is identity. Okay, and now, well, so as we already noticed, omega is symmetric. So we've already noticed that. That's literally the same computation involved in, I don't know, I think it was here, something like that. Yeah. So in the case when this is 0, then M should be symmetric. We're allowed to add a symmetric term here. So that's what the result says. So the result is that there is some, this L prime, this complementary Lagrangian subspace will be spanned by some vectors incorporating all of the F's, in which the corrections has to be via a symmetric matrix. Okay. Now, I don't know if it's 2C, I guess it's 2C. Maybe it's a good idea to go to the next page. So we're given L varstrich in V Lagrangian with, and we are told that dim of L intersect with this is equal to K. Okay, so actually I have some different notes for this, where they are. You have to do it from memory. No. Okay, so I don't seem to have my notes. They'll probably be a little bit more messy, but never mind. So let's choose a basis. E1 to EK for this subspace, right? So L intersection L prime. And it's K dimensional, so there are K of them, and extend to a basis for L. So I write L equals the span of E1 up to En. Okay. Okay, now right, so now I must have, so we have so this is a any vector, any vector that can be expressed in any combination. So we have E double prime, so that's the basis for L double prime. It can be written like this. And some complementary set, which we're not going to need. It's equal to E B plus FD, where these matrices satisfy the condition which we found for SPV. Okay, and now we have that we have A as this form, IK. So it's this block structure. You can write alpha beta. And C is 0, 0, gamma, delta. Okay, so that's what we have from this assumption. From this basis that we've chosen, it's not an assumption, it's fine. So now, let's just go back to, otherwise it will take too long. We've got A transpose C minus equals C transpose A. Right, okay. So we've got A transpose C minus C transpose A equals I alpha transpose 0 beta transpose. And here I've got 0, 0 gamma delta. By the way, delta is not a very good, okay. Delta is not a great thing to use. Let's choose phi instead. Okay, minus 0 gamma transpose 0 phi transpose I alpha 0 beta. If I write them all down, I've got 0 0 minus gamma transpose gamma. And then here I've got beta transposed phi minus phi transpose beta plus alpha transpose gamma minus gamma transpose alpha, right? Okay, and this is supposed to be 0. So that's supposed to be 0, it means that gamma is 0. And as gamma is 0, those things disappear. And beta transpose phi is equal to phi transpose beta. Okay. So in other words, we have that L, so we have, just a minute, we have so again, now we can suppose without loss of generality that phi equals the identity. So why is that? How do we suppose that? Why can we suppose that this is? Can you suggest? Is Anton the only person left here now? It's not impossible. I don't hear anyone else. So
I think there is a much easier way to do
okay.
And kind of was.
Well,
so
can you just answer my question? Why can I assume without loss of generality that phi is the identity?
I am kind of lost in notations again. Too many letters. Phi is no. For me, to be is about. I think it can be solved without using that this subspace is Lagrangian. Maybe a counterexample will help me if we are doing it.
Sorry, you want me to give you the, all right.
Oh,
I have 8 people still with me. I hope they are really still with me. Anyway, Anton, I'm going to give you, so you have the right to share your screen. You should have it anyway.
yeah. So what I want to say, I really want to do this. Yeah, and then this. So we have some complementary subspaces like yellow color. Sorry, how do I switch colors?
Right.
So L plus L prime equal to V, dim L equal to.
I don't see
dim.
anything, Anton.
Oh, and now can you see right color?
Okay, okay.
So dim L is equal to dim L prime and then equal to N and dim V.
But I'm sorry, wait a minute. You're doing a different problem then.
Oh, sorry, maybe it's the way
You're doing the case when the intersection is 0, right?
Now intersection is not 0, yeah, okay. So if intersection is not 0, I think this follows from idea that our procedure for making like this basis for whole V. So remember, there was lemma if x1 etc xn is basis for L,
yes,
exists y1 etc y1 that this whole thing
I don't know why you're able to write so much better than me on the tablet.
What?
I wish I was
using-
able to write so clearly on the tablet. I don't know how to solve this. Anyway, go on then. Yeah.
Maybe I will show you.
Maybe you will
things
show me. Yeah, that
you
would
need
help.
to buy. Okay, so now idea is that to see momentally follows from this lemma, because we need just to have that x1, etc., xk, that like this linear span
Yes.
is intersection.
Okay. Yeah.
Yeah. So what is rest to prove? Rest to prove that I need to rearrange some first things here to get. So what I know now? Now I know that I continue this to basis in whole space. Yeah. I continue this to basis in L, so there exists basis and in L such that this thing is intersection. And now I continue this to symplectic basis for whole V. And now problem is that basis for A prime looks like x1, etc., xk, and then some linear combinations of this ways. So, like for example, we can, for example, if there is another vector, what can I say? So how can look this by? How can this basis looks like? I'm sorry, I thought that there can be no x's, but of course they can, and that's the reason why you have so much matrices. So let's give me a try. For example, there will be
well,
alpha.
as we discussed, Anton, you have the freedom to add combinations of x's, but only via symmetric matrices. The linear combination of x's involves a symmetric matrix.
So I want to rearrange this basis for first k vectors being just belong to L prime. So if y1, for example, belong to L prime, it's very good. Yeah, and what we want to, what is our freedom to move this y1, yn? We can like use any matrices from SP, yes? Or no? So I need to make.
So you can use any matrix from SP which doesn't change the x1 up to xk.
Yes, and now.
Which, by the way, is exactly what I was writing, even if it was. I mean, I hope you can see that that's exactly literally what I was writing. It may not have been understandable with the bad notation, but it was literally what I was writing.
Yes, I was just distracted to try to do this by myself and made a mistake. So sorry. What? So we need still. So there is like other Lagrangian complementary subspace. So this whole thing can be like some, I don't know, X, which is Lagrangian. Yeah, we proved this.
I'm afraid we lost nearly everybody. We have 6 people left, including me. Anton, the thing is, Anton, look, let me just suggest, because this is a little bit painful on Zoom to do it like this. When we meet in the auditoria, this is exactly what I want to do. This is what is more interesting. This kind of discussion is exactly what is interesting. But unfortunately on Zoom, you can see we lost everybody. Because
I
nobody
have-
listen to this. It's too.
I have
frustrating.
solved it and I can speak
Yeah.
it very fast. So there
Go
is
on,
like
go
basis for V that consists from vectors from two Lagrangian spaces. And
Mhm.
if dimension here is K, dimension here, like, let me write V equal
Mhm.
L plus double V.
Mhm.
And now L prime cap L has dim K.
Mhm.
It will yield that L prime cap double V has dim n mean 2n mean minus K. Yes, yes.
Okay.
So now we just fix any basis here, and getting the basis of big spaces. No, it's not equal, I think. Like, because like after that we will get form like 0 here because this both coordinate, but I don't get this once.
Yeah. No, but the thing is, Anton, it's not so cheap. It's not so
It's-
easy. It's not. I understand what you want to say. You want to say that
It-
that you can do it in your way. But all I'm saying is that your way is kind of the same as my way. But because you didn't prepare it, you're getting lost because it's
Sorry,
just this
I'm
epsilon
sleepy
non-trivial.
now because it's like 18:07
Yeah.
of time.
But
So,
let's listen,
okay,
Anton.
okay,
we will
let
meet
me stop.
in the future. We'll meet in the auditorium. Everything will go much better. So, what do we have left to do? We have nearly lost everybody anyway.
So maybe it's enough for today because
I'm
it's
afraid
really
so. I'm afraid so.
time.
So I'm going
Okay.
to send messages to people. There is 5 people left. I'm going to stop the recording.